Let me see. So polar just gives us a polar coordinate system is a coordinate system like the rectangular coordinate system, which helps us to identify locations of points on a plane. And when you expand it to 3 space, can help you with what are called cylindrical coordinates as well. But in our normal rectangular coordinate system, if we want to identify a point in space, the rectangular coordinate system is based on 2 number lines, which we call the x-axis and y-axis, and those 2 number lines together are put perpendicular to each other so that every point in space can be identified by a representation along the x-axis and y-axis. So every point in space in the rectangular coordinate system is identified by what we call an x-coordinate and a y-coordinate, right? So we know that. That's the one we use all the time. And if you look at rectangular coordinate paper, right, what is it? It's when you graph paper using the rectangular coordinate system, what are you getting? You're getting a bunch of squares or rectangles, right? And that's hence why it's called the rectangular coordinate system. It's based on identifying points in relationship to the edge of a square. In the polar coordinate system, which is what we're learning about today, there are 2 basic elements. Well, actually, there's one basic element around which the entire system is built. So instead of having an x-axis and y-axis, there's simply what we call the pole. And the pole is what everything is built around. The pole is like the origin. So if you were to put the pole onto a rectangular coordinate system, it would be stuck right there in the middle at the origin. And then if I have any point in space, so just put a point in space, we don't have an x distance and a y distance. Instead, every point in space is represented by an r coordinate and a theta coordinate. R being the distance from the pole to the point, that's your r, or radius, right? And it's actually a directed distance, meaning we have positive and negative. So I'll call that a directed distance from the pole. That's what r is. It's a directed distance from the pole. So I guess I'll just... Yeah, kind of. And we'll see what a minus r does in a minute too. But yes, it's based pretty much on the vectors, distances. And so theta, we're going to go back to trigonometry, where we start at an initial side, and that initial side coincides with the positive direction on the x-axis. And angles are built just like in trigonometry, wherein positive angles move in the counterclockwise direction and negative angles go in the clockwise direction. So it's just like how we do trigonometry. So theta is that angle that starts at the initial side and terminates into that ray that runs from the pole to the point. So once we have this set up as our initial polar coordinate system, well, then we need to get used to it. And so since this is pretty new to everybody, I want us to actually plot some points. Just so we get used to it, we get our fingers and hands dirty, we kind of get used to what we're doing here. So let's plot some points then. If you guys all had done these before, I would have skipped this part, but I think this is really important that we can understand what polar coordinates do, especially if you guys are going on to Calc 3. And also engineering. I think you guys might use polar curves. I don't know if you do or not. And I'm not sure, I have to start looking for applications in bio and chemistry and things.
I don't know if Civil has to do it.
Say what?
I don't think Civil has to do it.
You don't have to do polar at all?
I don't think so.
Nothing
It
circular?
depends what you're doing. If you're doing, you're actually in the field, like at a job site possibly.
Yeah.
Most civil engineers just fill out forms and
A lot of your equations of motion.
Yes, they are. A lot of motion equations, cycloids, any time of movement are often built in, and actually anything circular can be built around cosines and sines. Actually, anyways, yeah, absolutely. So here we go, ready. So we're going to plot each point. So when you get your point, the first point we're going to practice right here is 2 pi over 3. 2 is my r, pi over 3 is my theta, and when you plot a point, and I gave you guys all polar paper today if you want, or you can just draw it, but I like this polar paper. You can download it if you're taking notes on an iPad or something. You can actually just Google polar paper, and if you want this specific one, which I really like, you can let me know, and I can send you the whole PDF if you want. But the polar paper has angles on it, and it's got circles on it, right? It's got angles and circles. Because when you go to plot this thing, your units are going to be based on angles and circles. The first thing I do is I find my angle. And so we want pi over 3. So the angle pi over 3 is right up here. And then after I find my angle, then I plot a radius. So I say in the direction of pi over 3, I want to go 2 circles out, or 2 units out, and that's going to give me that point. So you should have 2 circles out. That should be the point 2 comma pi over 3. Does that make sense? So why don't you guys graph for me then 3 comma negative pi over 2. And tell me where you wind up.
That'd also be 3 pi over 2.
We're going to talk. Oh, I like that, James. I like that. We'll talk about that in a second. Different representations, right? Absolutely. Absolutely. So negative pi over 2 is here. Negative pi over 2 is this distance down here. And radius of 3, going in the direction of negative pi over 2, I have to go 3 units out. And so that puts me down here on the bottom, right? 3 comma negative pi over 2. You guys agree? Everything okay so far? Now, r is not restricted to be positive. R could be negative. R actually could be negative. So what would we do if we have the point negative 1 comma 5 pi over 6? Negative 1 comma 5 pi over 6. Again, I always start with my angle first. Negative 1 comma 5 pi over 6. Oh, I like it. Okay, so we've got, let's see. We've got this angle here, which is negative 5 pi over 6. No, sorry, which is positive 5 pi over 6. Sorry about that. And we've got a radius, though, of negative 1. And so when we talk about positive radiuses, they go in the direction of the angle, right? So positive radiuses would be heading towards 5 pi over 6. Negative radiuses actually go on the opposite side. So you head to 5 pi over 6, and then if you want to get a negative radius, you have to go to the opposite side. That gives me negative radiuses. So if I'm going to plot negative 1, 5 pi over 6, I first go to 5 pi over 6, and instead of going 1 unit in that direction, I go 1 unit in the opposite direction. Does that make sense? Do you guys see how that works? So that point down there is the point -1 comma 5 pi over 6. And why don't you try this one? Tell me where this goes. -2 comma negative pi over 4. -2 comma negative pi over 4. Do your angle first and then do your R value. But because your R value is negative, make sure you go to the opposite side. What quadrant did you wind up in? Oh, wait, try again? Wait.
For what, -1 or 5
-2 negative pi over 4.
-2
Negative pi over 4? And then, oh, I know. You guys all set, you're saying over here, right? And when we do quadrants, we go 1, 2, 3, 4. We go backwards, just like we do with unit circles. So this guy is quadrant 1, this guy is quadrant 2, this guy is quadrant 3, this guy is quadrant 4. I think you guys actually had the point in the right place. So -2 comma negative pi over 4. Did you guys all get a point up here in quadrant 2?
Yeah.
Yeah. Does anybody have questions on plotting points or how the polar coordinate system works with points? What's interesting is when you're graphing things, sometimes you wind up on the opposite side of where you think it should be. So that is something that actually happens. And not only that, but yeah, James pointed out something, that every polar point can actually be represented in multiple ways. There's different representations. For instance, right there at the very beginning, let's do 3 comma negative pi over 2. There are more representations for that point. So instead of writing 3 comma negative pi over 2, we could have written 3 comma 3 pi over 2. Can you guys give me a couple more? How else could we write it? What else could we do? Give me another representation for this point. 3 comma 5 pi over 2. Go all the way around 2 pi and add another pi. Oh, wait. Negative 5 pi over 2. 3 comma negative 5 pi over 2. I like it because we go all the way around the circle, negative 4 pi over 2, and then another negative pi over 2, negative 5 pi over 2. Or 3 comma, 7 pi over 2, right? So we go all the way around the circle in the positive direction, which gives us 4 pi's over 2's, and then add another 3 to it. How about with a negative radius? Can you guys give me a negative radius answer? Negative 3 comma pi over 2. How about another one? Negative 3 5 pi over 2. How about a negative radius and a negative angle? How about negative 3 pi over 2? Yeah, because it goes all the way around, right? Negative 3 pi over 2, and then negative 3 brings it back down again, right? Negative 3 pi over 2 shoots me here, and then negative 3 brings me back down again. Yeah, very good, very nice. So, something to recognize is that every polar point can be represented in multiple ways. Actually, the list would go on. We could keep listing, but just be aware of that. Your radius can be positive or negative. It's positive in the direction of the angle. When you plot a polar point, start with the angle first. Okay? So let's talk then about equations. So these are points, but let's talk about what polar equations look like. Because r and theta are our basic coordinates. These are the basic coordinates in the polar system. It would make sense that the equations involve r's and thetas. So what do each of these curves look like? Let's look at this first example here. What if I wrote r equals 3? What do you think r equals 3 is?
It's going to be a circle of 3.
So r equals 3, what is this? This means the radius is always 3 units away from the pole, right? And so if you can envision when you're in polar coordinates, if I want to go 3 units away in every direction, right? That's simply going to give me a circle. And so r equals 3 is how we would write the equation of a circle. So r equals 3 is the equation of a circle in polar coordinate system. R equals 3 is a circle centered at pole of radius 3. What if I wrote something like this? Theta equals pi over 4. What do you think that describes? What do you think theta equals pi over 4 describes?
She just wrote a diagonal line.
So what it says is that the angle is always pi over 4, right? So this tells me my angle is pi over 4. Doesn't specify what the radius is, but I could have any radius. And so if you go and you take the pole and you go to an angle of pi over 4, that right there gives me an angle of pi over 4. It is just a line, and that line just is at 45 degrees, or pi over 4. So the equation for theta equals pi over 4 is just a straight line. Okay, well, those are simple curves. Those are simple curves. What if we get some more complicated curves going? What if I wrote something like this? R equals 4 cosine theta, or r equals -1 plus cosine theta, or r equals -1 plus 2 cosine theta, or r equals secant theta. Okay, so what happens when I start putting r's and thetas together? Then what do these curves look like? Well, now, if we were doing this by hand, learning this for the very first time, which we kind of are, but if we were in a pre-calculus course, we would set up a table, and we would look at r's and thetas, and we would pick a bunch of theta angles, probably 0, pi over 6, pi over 4, pi over 3, pi over 2. We'd keep going. We'd pick a whole bunch of theta angles, and then we would find what r is in relationship to theta. And we'd get all these points, and then we'd plot all those points, okay? Graphing polar curves takes hours. No, really, it takes hours, because these are curves that fold on themselves, turn around, sometimes make loop-de-loops, okay? These curves are very unique, and so it can take hours to do these. So on your tests, I will not ever make you graph a polar curve, okay? We're in calculus 2. We're going to explore the calculus of polar curves. So I will always give you a Desmos graph. So if you have a computer or a laptop or a phone, if you want to pull it out right now, we're going to explore some of these graphs. So I don't know if you guys have anything or a utility. Do you have any laptop or anything with you? Pull it out. Throw it out if it has computer battery.
Yeah.
If you want. You don't have to. You can just watch. You don't have to. Absolutely
Are you
not.
doing it on the big screen?
I am.
So if I just watch that.
I'll do it on the big screen. Huh? Sometimes when you do it as you do it, you get practice though, but that's okay. You can watch. Absolutely. Yep.
Well, you'll give us a graph on the test, right?
On the test, I'll give you a graph.
Made, right?
But on your homework, it won't be made. Yeah. And you'll have to be able to, you know what I mean, understand. So what I want you to do is I have 4 graphs right there. We're going to look at those 4. We're going to look at a couple more, actually. We're going to look at a couple more. So we're going to look at r equal 4 cos theta. But then I also want to explore, okay, well, what's r equal not 4 cos theta, but 6 cos theta? What's r equal 10 cos theta? What's r equal 4 sine theta, right? So I want to look at different families. Instead of r equals -1 plus cos theta, maybe I'll look at r equals -1 plus sine theta. What does that look like? And maybe I'll look over here, -1 plus 2 sine theta. Maybe I'll look at -1 plus 3 sine theta, right? So we're going to look at a couple different things here. Then I'm also going to look at two other curves that I haven't written down yet. I'm going to put down also curve G and curve H. We're going to go over to Desmos here, but we'll also look at something like r equal cos 2 theta, r equal cos 3 theta, r equal cos 4 theta. And we're going to look at something like r equal theta. Okay, so we're going to look at a whole bunch of different curves here. We're going to explore them with Desmos. We're going to see what they look like, and we're going to put names to them, okay? We're going to put some names to them. So let me go on over to Desmos, and we'll do some work there. Okay. Looking at these in Desmos, you're simply typing the word theta. So r equal 4 cos theta, r equal 6 cos theta, r equal 10 cos theta. Type the word theta. Now, in Desmos, notice what's going on. First, we have this guy here. We're used to seeing this for parametric curves. This is like our parameter. And notice there's a range put automatically on that parameter. Desmos tells you what is the range in order to go once around the entire curve. So this range here tells you how long it takes to get around one rotation around that entire curve. Now, John, what are these? What are these things that we're getting when we type 4 cos theta, 6 cos theta? What kind of picture are we getting? They're circles, right? And so, for instance, this circle 4 cos theta, what can you tell me? What's its center point?
It'd be 2.
The center is 2, 0, right? And what's its radius?
It's going to be
2, right? So the center is 2, 0. The radius is 2. 6 has a center at 3, 0 and a radius of 3. 10 has a radius of 5. What happens when you type the sine in there instead? What happens to that curve if we get rid of the cosine, but instead we type 10 sine theta? What does it give us? It gives us a circle, but it's now on the y-axis as opposed to being symmetric about the x-axis. This one's symmetric about the y-axis. So we get another circle, right? So these guys here at the very beginning are all circles. 4 cos theta, 6 cos theta, 10 cos theta, 4 sine theta. They're all circles. How about the next guy? The next one we're having us do is -1 plus cosine theta. -1 plus cosine theta. What is that? It's not quite a circle, is it? Negative 1 plus cosine theta gives you, okay, so my old lacrosse students, Bobby and Braden and Ben, what do you think they called that? Well, you don't want to know what that's called. So we call this a cardioid. Notice it's like a heart, right? It's a cardioid. It's a heart-like shape. Negative 1 plus cos theta gives you a cardioid, flanks the x-axis. If you throw negative 1, r equals negative 1 plus sine theta, what do you think it does? What do you think it does? It's another heart. Where do you think it goes? On the y-axis, right? So the cosines tend to flank and be symmetric about the x-axis. This cardioid symmetric about the y-axis, right? Those guys are cardioids. Now, we put in front of them a 2. What happens when you put a 2 in front? What does that give you? Oh, it's kind of this weird loop-de-loop shape, isn't it? This guy's called a limason. I'm probably pronouncing this horribly. I'm also writing it horribly. Limacon, and it's got, I forget what you call that. What do you call that when you put the little thing underneath this? Oh, you guys can't see this.
Yeah, I can.
I'm writing this over here. You guys can't see what I'm writing. The second one was called a cardioid. The first guy was a circle. Oh, I should be writing this down right here. Let me put it here. The next guy, I'll add a note here, is called a limason. Except it has underneath the C, it has, what do you call those things when you put them to make them sound like S's? Or
I don't know what they're called.
Does it make it sound like an S or a cup?
No, it should be S.
I think it makes it sound like an S.
Regular is going to be limaton, but this is
Yeah. They're curlicues. And if you increase that number, notice it kind of makes it bigger and it expands that circle, right? It just expands it. And if you did sine instead, then you know what? It would loop-de-loop on the, it would just loop-de-loop on the y-axis, right? So do you guys see what I mean when we play with these a little bit?
That's something interesting playing with this.
What did you find?
So if you take that initial value there,
Yep.
and you make it way smaller,
This one here, instead of 3 1/3, or do you mean negative 1?
the negative 1.
Negative 1 and make it small?
But if you get below an eighth,
Interesting.
it becomes like a disconnected spiral.
Oh, interesting. It does what?
Remove the 3.
Oh, remove the 3. Okay. Oh, interesting. It does some funky things, doesn't it?
Mine is disconnected.
Yours is disconnected. Wait, why is mine not doing what yours does?
Yours is overshooting.
Say what?
Yours is overshooting.
Mine is overshooting. Show me what yours is doing. Oh, I see. Interesting. That is interesting. That is, well, I'll tell you what. Okay. That is really cool.
Yeah, so it looks like it's because Desmond's really graphs from 0 to pi.
Maybe, huh? I'd have to look and see what's going on with that, James.
It looks like if you increase the bounds of 2.
I was going to say maybe it's not catching all the bounds.
It's really weird that it happens right at 1/8.
I wonder why. Oh, is it because of 2 pi or 4 pi? Is it something to do with that, maybe?
Yeah, if I stick the 2 pi, then I get down to 1/16.
Huh.
See what happens.
What happens with r equals theta? What do you get when you type r equals theta? It's a spiral, right? R equals theta gives you a really cool spiral. How about cosine 2 theta? What's that give you? It gives you a 4-leaf clover. Sine 2 theta also gives you a 4-leaf clover. You want to send a note to somebody, go to Desmos, type in r equals sine 2 theta, and then maybe minus square root of x with a negative? Ha! Ha! Well, I have to bring it down a little bit. Maybe I'll expand that a little bit and put a 4 on it. Will that make it a little bigger? There we go. Ooh, I wonder if I put a less than or equal to. Oh, hello. Well, that didn't do what I thought it did. Probably because I have to worry about negatives when I put a less than or equal to in there. So how about we do less than or equal to sine of 4 theta. There we go. Now we got a 4 theta. But anyways, stop. Tina, stop playing. Okay. I could sit and just play with these all day. But what happens, so r equals sine 4 theta gives you this. R equals sine r equals sine 6 theta gives you this. R equals sine 2 theta gives you this. These guys are called roses. Have you ever heard of the rose curve? The rose curve is a polar curve, and it's like a rose. It's like petals. Now, what do you notice about when you have an even number in there with your theta? 4 theta, 6 theta, 2 theta. Cosine of 4 theta gives you how many petals?
2 in each quadrant.
Yeah, it actually gives you 8 petals. Do you notice that? Cosine 2 theta or sine 2 theta gives you 4 petals. So it actually doubles the number, 2 in each quadrant, like you said, right? It's really interesting how it comes out, these curves. These guys are all called roses. They're all called rose curves. What's interesting is if you put an odd number in there, so if you actually put odd numbers in there, it matches the number of petals. If you put a 5 in there, it gives you 5 petals. If you put a 7 in there, it gives you 7 petals. 3 in there gives you 3 petals. So what's interesting is when that number in there is odd, it actually matches the number of petals. It's really kind of interesting. So 5 gives you 5 petals, 3 gives you 3 petals. And to make them bigger, you throw numbers in the front. So if I put a 4 in front, that just makes everything go out bigger, 4 units. So the petal will touch here, but it'll come out here, 1, 2, 3, 4 units. So rose curves are actually one of the most powerful or common curves that you see when you talk about polar curves. They're all called roses. Now, our job is not to graph these things. Again, we're in calculus. But what I want you guys to see these cool shapes. Our job is going to be, for instance, find the arc length of the curve. How long is that curve? Or find the area in one of the petals of a curve. Okay? So our job, or find the slope and the equation of a tangent line at any given point. So we're going to put calculus to this. But it's important that we at least take a little bit of time to explore and look at these things so we see what polar curves look like, right? So we see how they work, what they do, things like that. There was one other curve I wanted to look at. That's r equals secant theta. And I like this curve as the last curve. What is r equals secant theta? What is that curve? It is a vertical line at 1. Why?
Because
Why?
secant is 1 over.
It is. It is. It is. I like where you're going, Max. Secant is 1 over cosine. I like where you're going. So let's go to our laptop. Yeah, let's talk about this. R equals secant theta is a line, x equals 1. Why? It does have to do with something with cosine, because secant is 1 over cosine, but it also has to do with a little more. And I really like this example because it's a motivation to tell us that, all right, well, now that we've looked a little bit at polar curves and see all the funky, fancy, cool, neat things, today's St. Patrick's Day, you should send somebody a Desmos. You should send them a 40 clover, right? You should send them a 40 clover. But anyways, maybe not. But I think that's cool.
And by the way, cosecant makes horizontal lines.
Cosecant makes horizontal lines. Yes, it does. Y equals. Yes, it does. Yes, it does. So, how are we going to relate r theta, x's, and y's? That's where we're going right now. There is a relationship between polar coordinates and rectangular coordinates. And that relationship, and talking about that relationship, is necessary for finding area of curves, finding dy dx. We need to talk about that relationship. So that's where we're going right now. So let's explore the relationship, and then we'll go back to the secant curve. Let's explore the relationship between rectangular and polar coordinates. So we're going to look at the relationship between rectangular and polar coordinates. So let me draw my point again. And let me attach to that point an r value and a theta value. And pictorially, that means this distance is r, and this angle is theta. Now, on top of that, let me superimpose the xy plane. And if I do that, this point here in space can also be represented as an x and a y coordinate, where x is this distance and y is this distance. Y is the vertical distance and x is the horizontal distance. And so if I want to find a relationship between those two coordinate systems, namely the polar coordinate system and the rectangular coordinate system, I can kind of, not just kind of, but I can relate back to that right fundamental triangle, or that right triangle, excuse me, where x is the horizontal, y is the vertical, r is the hypotenuse, and there I can write all kinds of relationships. For instance, I can write Pythagorean theorem. What's the Pythagorean theorem? A squared plus b squared is c squared. Do it for my triangle, Drew. What's my triangle Pythagorean theorem going to say?
X squared plus y squared equals r squared.
Awesome. Absolutely. Ooh, what's my tangent? Something over y over x? Ah. What's my cosine? What's my sine? SOHCAHTOA. Sine is what? Sine is y over r, opposite over hypotenuse, right? Opposite over hypotenuse. SOHCAHTOA. Cosine is adjacent over hypotenuse, right? So from that right triangle, we have all these relationships. And the key ones are the ones, well, all of these are key relationships. But two in particular help us a lot, and that is if we take cosine theta equals x over r, you should see that x is also r cos theta, and y is r sine theta. And these are kind of the ones that I really, really like and help me and motivate me when I start to do my slope and my area for polar curves. But these also inform us. So, right, we said that r equals secant theta is a vertical line, and now we can talk, or r equal cosecant theta was a horizontal line, but specifically we said r equals secant theta is a vertical line, and do you see how that comes out to play? Because r, like you said, Max, is 1 over cosine. If you multiply both sides of my equation by cosine, I get r cos theta equals 1, and what is r cos theta? R cos theta is just x. And so, see, that relates everything. That shows us. And our cosecant of theta is 1 over sine, and our sine theta is y, and that's why they become horizontal lines. So everything all relates. It's just beautiful how it all comes together. You want to make sure this relationship is in your notes somewhere. If you're taking Calc 3, this is the basis for what are called cylindrical coordinates, and you're going to spend a lot of time going back and forth between cylindrical coordinates and x, y, z coordinates. Also helps you a little bit when you talk about your spherical coordinates, but that's more based on spheres versus the cylinders. So, but this is also the basis for what we call our calculus, namely slope of a tangent line and area. So the last thing we're going to do today is we're going to talk about the slope of a tangent line to a polar curve. Do you want me to go back? Are you guys okay? Did you get all those relationships? Let me go back a sec. Did you guys get all those down? Make sure you copy all those relationships down. X equals r cos theta, y equals r sine theta. Those are the key ones right there. And they come from that triangle. And then we're going to talk about the calculus. All right, so slope of a tangent line to a polar curve is dy dx, right? Okay, and we just got done doing parametric curves. Okay, so the parameter in parametric curves was t, right?
Yeah.
So how did we, John, how did we get dy dx with it if we had a t involved as our parameter? What did we take?
Or derivative top of
We took dy dt
yeah, and then
divided by dx
yeah.
dt.
Yeah. And
Yep.
then,
And then we do all that stuff,
yeah,
right?
like the whole
Okay. So if you have dy dx, we just did dy dt over dx dt. Y'all with me? So for polar curves, okay, stay with me. John, what do you think? What's our parameter with a polar curve? Not t, theta. So how do you think we take dy dx? We take dy d theta over dx d theta. Now that's all fine and dandy. That's all fine and dandy, except remember our polar curves look like things like this. R equals cos 4 theta. R equals -1 plus 2 sine theta. So what are we going to do with the y's and x's? Because we don't have an x and y. Whereas with parametric, we did, right?
put them as r's. Or
You're getting really close. We do know what x is equal to in terms of r and theta, don't we? And we do know what y is in terms of r and theta, right? So let me just erase these, okay? And let's do this. I know that x equals r cosine theta, thanks, Andrew. And what is y? Y equals r sine theta, right? Okay, now, I also know that for our polar curves, like for instance, r equals -1 plus 2 sine theta, I also know that r is itself a function of theta, right? R depends on theta. So what that means is r is a function of theta, cosine is a function of theta. So if I want to find dx d theta, oh my goodness. So if I want to find slow down, Tina, undo. So if I want to find, and I'm going to erase this and give me more space. If I want to find dx d theta, and if I want to find dy d theta, I'm going to go back to this relationship here with x equals r cos theta, y equals r sine theta. And I'm also going to use the fact that r itself is a function of theta. And so if I want to take the derivative of x with respect to theta, I have to recognize I've got a product involving two functions of theta. R is a function of theta, and x is a function, and cosine is a function of theta. So if I have a product involving two functions of theta and I take a derivative, I have to apply the product rule.
Oh, so a few times too.
I have to apply the product rule. So let me just put a little note here. We have to apply the product rule because r is a function of theta and cosine's a function of theta. Okay, product rule. Derivative of the first times the second, right? So we have our first function, our second function. Derivative of the first times the second. Okay, how are we going to write the derivative of r with respect to theta? We're just going to write dr d theta. So derivative of the first times the second plus the derivative of the second. I'll get rid of that. What's derivative of cosine? Negative sign. So derivative of the second times the first, which is r. So if I have x equals r cos theta, then the derivative of x equals r cos theta with respect to theta is just dr d theta cosine theta minus r sine theta. Does that make sense? Same thing down here. R is a function of theta. Sine is a function of theta. So again, I have to use the product rule to find the derivative of y with respect to theta. Okay, so derivative of the first times the second plus the derivative of the second times the first. So derivative of r with respect to theta is dr d theta times the second plus the second, plus r times the derivative of sine theta, which is just cosine theta. Now, why is this going to help me? Because, believe it or not, it's weird. I know it's weird, but to find the slope of a tangent line to a polar curve, you actually have to rewrite as dy d theta over dx d theta and then substitute. So what you have to do is this. You have to use this formula. Dr d theta sine theta plus r cos theta divided by dr d theta cos theta minus r sine theta. This right here is the formula for finding the slope of a tangent line to any polar curve. Dr d theta sine theta plus r cos theta over dr d theta cos theta minus r sine theta. It's huge, it's messy, and we're going to do two problems to work through this, okay? This, put in your notes, star it, blanket it, put it big somewhere. This is the formula you always use to find the slope of a polar curve, okay? Dr d theta sine theta plus r cos theta, dr d theta cos theta minus r sine theta.
You just substitute them with r then?
Yes. So now we're going to, let's do an example. Okay, so let's do an example. Here we go. Ready? Let's do the following. Let's actually take, I don't know how this will work out because I haven't done it, so I guess we could try it. I don't ever like to try things that I don't try ahead of time, but heck, let's try it anyways. It probably is going to go awry, but we can do this. But let's do the following example then, okay? let's do the example. Let's find the equation of the tangent line to the curve R equals, might as well just try the one I have up here. Who knows what this is going to turn out to be. R equals -1 plus 2 sine theta at the point theta equals, what should I make it? I guess I could do pi. Let's do pi over 2. See if this works out okay. I have no idea what this is going to become. I probably just made it undefined there. Let me see. What do these guys look like? -1 plus 2 sine of theta. Maybe not. Ooh. Well, we'll do it anyways. We'll see what this does. See how this works. I have no idea how this is going to turn out, but we might as well do it. All right, here we go. Find the equation of the tangent line to the curve. R equals -1 plus 2 sine theta at theta equal pi over 2. All righty, so what's the first thing we need to do to find the equation of a tangent line? We need to find the slope, right? We need to find dy dx because we need the slope of the tangent line. So the very first thing we need to do is find the slope. Here we go, here we go, here we go. So we want to find dy dx, the slope. But I know what it is because we just copied it down in our notes and we just developed it. It's dr d theta sine theta plus r cos theta over dr d theta cos theta minus r sine theta. And just so we have a visualization going on here, I will show you what picture we're looking at. We're looking at this picture right here. So this is r equals -1 plus 2 sine theta. I should have done a 4-leaf clover, but that's okay. All right, so the key pieces. Sine theta is just sine theta. Cosine theta is just cosine theta. So those we just leave as they are. But like you said, Andrew, what we have to do is we have to replace r with the function r. And we have to replace dr d theta with the derivative of r with respect to theta. I know what r is. R is given to me. It's right here. I can get dr d theta. Alrighty. So if r equals -1 plus 2 sine theta, what's dr d theta? You want to get me that derivative, John? What's that derivative, huh? So what's the derivative of r with respect to theta? What's that going to give us? Derivative of -1 is 0, right? And then plus 2, right? What's the derivative of sine?
Cosine or cosine?
Positive cosine. Derivative of sine is cosine. So did you get 2 cos theta as your derivative? Nice. So we're going to plug that in, and that's going to tell us that dy dx, or the slope, is 2 cosine theta times sine of theta plus r, which is -1 plus 2 sine theta times cosine theta, all divided by, again, dr d theta, which is 2 cosine theta, minus r again, -1 plus 2 sine theta. I think I did that right. Make sure you guys agree with me. we put r in for r, and we put our dr d theta in place of dr d theta, and we left a sine where it was and a cosine where it was. Is that what your guys' look like? Now, we could do a little simplifying, and you would get 4 cosine theta sine theta minus cos theta on top, and 2 cos squared minus 2 sine squared plus 1 on the bottom. We could simplify this down, but we don't need to, because we're just asked to find the equation of the tangent line to the curve. So that means specifically we want to find dy dx at the point theta equals pi over 2. So we could just plug pi over 2 now into that derivative. So that's going to give us 2 times the cosine of pi over 2 times the sine of pi over 2 plus negative 1 plus 2 sine pi over 2 cos pi over 2 all over 2 cos pi over 2 cos pi over 2. Like I said, you could use a bunch of trigonometric identities and simplify this down. But yeah, because a lot of these go to 0, don't they? Because the cosine of pi over 2 is 0, right? So a lot of these are going to go to 0. And the sine of pi over 2 is just 1. So really, what is this giving us? It's giving us 2 times 0 times 1 on top, plus negative 1 plus 2 times 1 times 0, all over 2 times 0. Oh, this isn't very interesting, Tina. This is why you never do an example off the top of your head. I had other examples in my notes, but I decided, nope, we're just going to try this one. But that's okay. Why do I say it's not very interesting? What are you guys getting as your slope? 0 over negative 2, which is just 0. So you guys are getting a slope of 0. Well, that's not fun. Find the equation of the tangent line to the curve. So, ugh. So my slope is 0. The equation of a tangent line is y minus y1 equals m times x minus x1. My slope is given to be 0. But let's just assume my slope wasn't 0. What if my slope was a half or 1 or 3 or something else that was nicer than 0? How would I go about finding the x value and the y value? What would you do? What would you do, Kayla? What would you do? How can we get our x? Yep.
We know theta.
Yep. We know theta.
And then we can also just solve for r.
Yep. So to get x, you can take r cos theta, and to get y, you can take r sine theta. Yep. And for our curve, what is r? I can't seem to make this any smaller. Sorry about that, guys. So r is negative 1 plus 2 sine theta. Yeah. So to get x, or our x sub 1, we're going to take negative 1 plus 2 sine of pi over 2, because that's the angle, times the cosine of pi over 2, which is 0. So my x value also becomes 0. My y value is negative 1 plus 2 sine pi over 2 times sine of pi over 2. That's going to give me negative 1 plus 2 times 1, which just gives me 1 times 1. And so that tells me y equals 1. And so that gives me my equation to my line. Y minus 1 equals 0 times x minus 0, or simply y minus 1 equals 0, or y equals 1. And if we look at our graph, what's happening in Desmos, and I'll show you, I'll go over to Desmos in a second, but what's happening is we have this loop-de-loop, and we are finding the tangent line right there at that point. So if I go into Desmos, let me show you Desmos. If I go into Desmos just very quickly, y equals 1 is the tangent line we got. What we are doing right now is finding the equation of the tangent line right here when theta is pi over 2. It's giving us this equation right here. We could pick one here, pi. We could pick one at pi over 3. I should probably have done a different one, but I wanted to make it as simple as possible here. So we've got y equals 1 is the equation of the tangent line. But the steps are going to remain the same. To get the equation of a tangent line, we'll take dy dx, and then we'll use y minus y1 equals m times x minus x1. And anytime you need to find x and y, when you have polar involved, you're going to use x is r cos theta, y is r sine theta. Okay, guys? You will have a question kind of like this possibly on your test, probably, and also on your recitation next week, okay? Did I tell you on the recitation next week, make sure you study question 1 from exam 2, okay? Because you'll get quizzed on it, and that score will be added into your exam score.
So when we're doing this,
Yeah.
when we're finding the tangent line,
Uh-huh.
like, in this case, the RD theta is just what, 4 cosine theta. Yeah, 4 cosine theta. Plus theta. Maybe 4 cosine 4 theta.
Let me see. Let me see.
It's just, that's,
General.
it would stay, like, so you do the outside, I mean, the inside.
Yeah, the inside just becomes a 4. And then we have inside times the whole thing. 4 cosine theta. Maybe 4
No, because the inside is 4 theta in this case.
So you guys are finding drd theta?
That's what you're thinking.
Ah, yeah, you got chain rule going on, right? Chain rule. Derivative of the outside times the inside. What'd you guys get? 4 cos 4 theta? Derivative of sine is cosine. Derivative of 4 theta is 4. R is sine 4 theta. So in place of R, everybody's putting sine 4 theta. And in place of drd theta, you guys are putting 4 cos 4 theta. Good. I'm going to wander that way. Let me know if you're... So yeah, because pi over 8 is not on your unit circle, you're just going to type it into Desmos. So we specifically want to find this when theta is pi over 8. So you're getting 4 cos 4 pi over 8 times the sine of pi over 8. Plus the sine of 4 pi over 8 times the cosine of pi over 8, all over 4 times the cosine of 4 pi over 8 times the cosine of pi over 8 minus the sine of 4 pi over 8 sine pi over 8.
So we just have to find the slope, we don't have to solve.
Correct. You don't have to write the equation of the tangent line. Though that would be fun. That would be really cool. Maybe, huh? Oh, except you can't really find it because it's pi over 8. So 4 pi over 8 actually cancels down to be pi over 2, right? 4 pi over 8 becomes pi over 2. So really, what you're doing is 4 times the cosine of pi over 2 times the sine of pi over 8 plus the sine of pi over 2 times the cosine of pi over 8 all over 4 times the cosine of pi over 2 cosine pi over 8 minus sine of pi over 2 over sine of pi over 8. And so what happens, what do you guys get happening? Cosine at pi over 2 is just 0, right? So these two terms drop out. Sine of pi over 2 is actually equal to 1. And so I think what you're left over with is 1 cosine pi over 8 minus 1 sine pi over 8. And I think I liked to write that as minus cotangent pi over 8. Though either of these will work. Because pi over 8's not on our unit circle and you're doing your homework, just type in pi over 8. So just type minus cotangent parentheses pi over 8. And that'll give you your answer. Go back to this one. That's going to give us negative cosine theta plus 2 sine theta cos theta equals 1. And it's going to give us negative sine theta plus 2 sine squared theta equals 0. I think I would solve this equation because it's easier to solve if I was doing this, Max. I would find my two thetas. Theta is pi over 2. It's actually also 3 pi over 2. And 2 sine theta would have to be 1/2. So that would put me up at pi over 6 or 5 pi over 6. So it could be one of these possibilities. And then I would see which of those worked in my first equation. Cosine pi over 2 is 0, so that gives me negative 1. So it's not that guy. 3 pi over 2 is 0. That doesn't, oh wait, slow down, Tina. That doesn't work either. Sine of pi over 6 is 1/2. 1/2 and negative 2 gives you 1. That's okay. Sine of pi over 6. Oh, wait, timeout. Cosine of pi over 6. Oh, no, this doesn't work either. Hang on, Tina. I got to think this through a little more. Hang on, hang on, hang on. Oh, we need that to go to 1. Oh, I got to think this through. Hang on, I got to think this through. All right, well, you guys, I know you guys have to go. You don't want to sit here and watch me do this. I'm going to figure this out. I'll figure this out for us. Yes. Yes. I see exactly.
Yeah.
Yeah, so now I can go back and do that other one. We talked, yep. So that will be the angle pi, and then, okay. I know, I make silly mistakes all the time too. Ta-da, right? Ta-da moments, and that's okay. We learn.